Alright, today I'm going to be explaining how batteries work on a very simple level. So we'll start with a very simple circuit, just a resistor and a battery. Let's say this is 1.1 volts, we'll see why later, and this is 1.1 ohms. So we know this battery is going to be pushing electrons through the circuit in this direction, which means conventional current is going to flow the opposite direction. But how is it actually doing that? Well, to find out, we can draw this battery in a bit more detail. This is what's called a galvanic cell, which you may recognize from your chemistry class. And this is how pretty much all batteries work. I'm going to be using a copper-zinc chemistry for this example, just because it makes all of the reactions nice and easy. But I don't think that's a chemistry that you would actually see in real life. So these are two electrodes of the battery. So this is your positive and negative terminal. This is actually going to be the positive terminal. This is going to be the negative terminal. So this is going to be copper electrode. And this is going to be our zinc electrode, each of which is floating in its own ion solution. This is a zinc solution. So this is the same resistor as before, right up here, 1.1 I wrote. So then we need what's called a table of standard reduction potentials. You can find this in any chemistry textbook. This tells us how much electrical potential each half reaction that we're about to formulate will produce. So this is one of our half reactions for the copper electrode side, and this is the other half for the zinc electrode. So we can see their corresponding reduction potentials over here. So the copper one we'll use as is. The zinc one will flip around to make the overall reaction have a positive voltage. So on this side we'll have copper ions reacting with loose electrons to form copper metal. So the metal is solid, which is going to be on the electrode, and the ions are in solution, which is in the solution. So this is in solution, and this is the electrode. Similar thing happening on the other side, but in reverse. So zinc metal, this is the electrode, is going to react into zinc ions and two loose electrons in solution. Alright, so the reduction potentials for each of these half reactions, on the copper side we have 0.34 volts, and on the zinc side we have 0.76 volts. It's negative in the table, but I'm writing it positive here because we've reversed the reaction compared to what's written in the table. So now we'll combine these two reactions together. So we have zinc metal plus copper ion forms, let's see, copper metal. Oops, let's see, right, that's a solution, so is that. Plus the aqueous zinc ion. So this is the total reaction that's happening in the entire cell. And to find the cell potential, we just add up the half reaction reduction potentials, and we get 1.1 volts. So what this is saying, if we look at what's happening in each of the half reactions, altogether this cell is going to be, rather, let's explain it in two halves. So what's happening on the copper side? So we have copper ion in the solution trying to react with loose electrons in the electrode to deposit solid copper metal onto the electrode. So essentially we're trying to suck loose electrons out of this copper electrode. And then what's happening on the zinc side? Well, we have zinc metal trying to react into zinc ions and loose electrons. So we're trying to push loose electrons out of this right zinc electrode. And the voltages just quantify how hard each of these reactions are pushing or pulling electrons. So in this case, they're both working together to push the electrons around the circuit in this direction with a combined strength of 1.1 volts. So in summary, that's how a battery works. You're using a chemical reaction to, in this case, take electrons out of the zinc electrode, in the process also forming zinc ions, which are going to fall off of the electrode into the solution. And then those loose electrons are going to be pushed out of the electrode through the wire, through your circuit, and absorbed by the chemical reaction on the other electrode, which in this case is copper, which will react with the copper ions in solution to deposit fresh copper on the electrode. So kind of as a byproduct, the zinc electrode is going to corrode over time and eventually disappear, and the copper electrode will grow over time. So, of course, this number, 1.1 volts, is an ideal number. You can see here at the top, this is standard reduction potentials, which means this voltage is only valid for standard conditions, standard pressure, standard temperature, standard, I believe it's 1 molar concentration of the ion solutions. So that's why, if you've ever noticed that batteries tend to lose voltage as they are used up. So what's happening is the solution is depleting on each side, which is changing these values away from the standard state, which will gradually reduce the voltage. But anyhow, that's a basic overview of how a battery works.